Okay, let's do a quick review of what we've learned so far in Chapter 6. So we talked about energy. We said that energy was the capacity to do work or transfer heat, right? And then just to remind everybody, work is energy that's used to move an object against a force. That force can be gravity, that force can be friction, a lot of different things. And heat is the energy used to change the temperature of a particular object. We said that there are two major kinds of energy. There are kinetic and potential energies. We said that kinetic energy is the energy of motion, and that in chemistry we're interested in thermal motion, which is the motion of atoms or molecules. And then we also said that for potential energy we're interested in electrostatic energy, which is which comes from really the interactions between charged particles. So this involves electrons, as well as the nuclei of different atoms. So this is what's involved in bonding or other electrostatic sort of interactions. And we said that kinetic energy, just in its most basic definition, mathematical definition, is 1/2 mass times velocity squared. So as the speed of an object increases, so does its kinetic energy. And we spent a lot of time in the ideal gas law chapter talking about this very relationship. In order to think about the energy flow between objects, we really need to orient ourselves and define a system and the surroundings. So the proportion that we single out for study, for observation, is called the system, and we call everything else the surroundings. And so when we study, say, the energy change that accompanies a chemical reaction in the lab, the reactants and the products are the system, and the container and everything beyond the container are considered the surroundings. We talked about open, closed, and isolated systems as well, just a brief review. An open system is something that can exchange mass and energy with the surroundings. So like an uncovered pot of boiling water. So heat is escaping from the water, right, as the temperature increases, but so is water vapor, right? So this is exchanging both mass and energy with the surroundings. We talked about a closed system. We said that it can exchange energy but not matter with its surroundings. So we gave an example of maybe like a cup of coffee with a lid on it. So eventually that coffee will cool down to room temperature, and so it's exchanging heat with the surrounding, but not any matter. So heat in the form of energy, or energy in the form of heat. And then we talked about an isolated system, and I showed a picture of a thermos. It's an imperfect example because an isolated system is rather ideal. It's saying that energy and matter can't be exchanged. But even a thermos will eventually, if you put hot liquid in a thermos, it'll eventually cool down to room temperature. Okay, so since we're interested in the change in energy of a system in chemistry, it's helpful to orient ourselves and think about what that change might look like. So we've defined internal energy, E, in class, so internal energy. And we said that it was the sum of all of the kinetic and potential energies of a particular system. And internal energy is all of the heat and work that is involved in a change in whatever system we're interested in. And so we can kind of conceptualize this as energy initially. So in a particular reaction, for example, there's an initial state of the system, and then there's a final state. And the final energy minus the initial energy gives us the change in energy. And so oftentimes we're thinking about the energy of the products minus the energy of the reactants. And we conceptualize this. First of all, remember we said that energy was a state function, and a state function is path independent. We're only concerned with the final and initial values. And we can kind of conceptualize this through an energy diagram. And in an energy diagram, energy increases on a y-axis, so let's consider A here. So this is the energy of a system here. We have an initial energy and a final energy. For this particular system, the initial energy is higher than the final energy. And we always say that a lower energy is more stable. And so if we have a lower energy here for the final state compared to the initial state, then the change in energy is going to be less than zero, and energy is going to be lost to the surroundings. So let's consider the alternative to this. The energy of the system increases. So again, we have increasing energy on the y-axis. We have a final state and an initial state. The initial state is lower in energy than the final state. Because the final state is higher in energy than the initial state, then the overall change in energy is going to be greater than zero. So energy is going to be gained from the surroundings in this situation. Okay, so a system can exchange energy with its surroundings in two general ways, as heat or as work. So the internal energy of a system can change in magnitude as heat is added to or removed from that system, or as work is done on or by that system. And so the variable we use to think about heat is Q, and the variable that we think about to consider work is W. The sum of heat energy and work energy will be equal to the change in internal energy. It's important to note that although energy is a state function, Q and W depend on the path or the process taken. And so one thing that you guys have to know is you have to know how to determine from the context of a particular question or a problem the sign of Q and W. So for Q, if the system gains heat, then that Q value is going to be positive. If that system loses heat, that Q value is going to be negative. So it gives off heat, negative, absorbs heat, positive. For W, if the work is done on the system by the surroundings, W is positive, and if work is done by the system, W is negative. If delta E is positive, that means that the system gained energy from the surroundings, and if delta E is negative, it means that the system lost energy. Okay, so let's look at an example of an internal energy change only involving heat. And this is an example I think everyone should be able to conceptualize. So let's look at A here. So A is an energy diagram. Again, on the y-axis, energy is increasing. So initially you have a cup of hot water. This cup of hot water has some initial temperature. This initial temperature is greater than room temperature. So this is what's happening initially. If you leave this cup of water out, eventually it'll cool down to room temperature. And the temperature of the system, this beaker of water, will equal the temperature of the surroundings, which is room temperature. So this means that the final temperature is, or the final energy is less than the initial energy. And so energy is less than zero, and its energy is given to the surroundings in the form of heat. So Q is less than zero. So for this example, Q is negative. Let's look at an example where Q would be positive. So if we have energy gained as heat in B, again, right, we have increasing energy on the y-axis. So initially we have a cup of ice water. And in this scenario, the temperature of the system is less than the temperature of the surroundings, right? So the ice water is colder than room temperature. And then if we just leave this out in room temperature, the final energy is going to be higher than the initial energy because this ice will melt and go back to room temperature. So in this case, the heat energy is gained from the surroundings, and that's what causes the ice to melt. So in this case, Q is going to be positive. Alright, let's look at an example. When gasoline burns in a car engine, the heat release causes the products, carbon dioxide and water, to expand, which pushes the pistons outward. Excess heat is removed by the car's cooling system. If the expanding gases do 451 joules of work on the pistons and the system loses 325 joules to the surroundings as heat, calculate the change in internal energy in joules, kilojoules, and kcals. Okay, so the place to start, we want to find the change in internal energy. Delta E is equal to Q plus W. We need to look at both W and Q and determine the sign here to plug it into this equation. Let's look at Q first. It says the system loses 325 joules to the surroundings as heat. So that means that this sign is negative, right? So heat is being given off in this reaction, so it's going to have a negative sign. So let's look at work. So the expanding gases do 451 joules of work. Anytime you have expansion, that means that a system is doing work on the surroundings, and so this is going to have a negative sign as well. So you have negative 325 joules minus 451 joules. So this equals negative 776 joules. So if we want to put this same value in kilojoules, let's make this a little smaller. So there are 1,000 joules, right, in every single kilojoule. So negative 776 joules times 1,000 joules for every 1 kilojoule. This is going to equal negative 0.776 joules. Okay, let's convert this to kcals. So you have negative 0.776 kcals. For every, for every, I just noticed that I wrote joules instead of kilojoules here too. Let me fix that real quick. This is kilojoules, right? So you have negative 0.776 kilojoules. For every 4.184 kilojoules, there's 1 kcal. So this will give us negative 0.185 kcals. So you have negative 0.185 kcals, negative 0.776 kilojoules, and negative 776 joules. So we also talked about in this chapter so far how to quantify heat. And so we talked about 2 different ways to quantify heat, which is Q. We talked about using the specific heat capacity, which uses the mass of a particular substance, and that is the formula for that is Q, which is in joules, is equal to mass, which is in grams, times the specific heat capacity, which is joules per gram times Kelvin, times the change in temperature, so T final minus T initial. We also said that you could use the molar heat capacity in finding Q, and so in this case Q would be equal to the number of moles times the molar heat capacity, which is joules per mole, times degrees Celsius, times delta T, and delta T again is T final minus T initial. So now that we know how to quantify heat, we can think about heat transfer between 2 different objects. So in lab, you guys had some water, and then you put a piece of hot metal in that. So this is the system, and then the water was the surroundings. And whatever heat the system had initially, it is transferred to the surroundings. So we can think about the heat of the metal, Q metal, and we can set it equal to the negative Q of the water. So whatever the Q of the metal is, the heat, whatever heat is lost, the water will effectively gain, right, that same proportion. And the signs are negative. The signs are different. The signs of the surroundings are negative to indicate that heat was transferred to the surroundings. The heat, of course, depends on mass of the water, mass of the metal, and then the specific heat capacities of both the metal and the water. And then temperature, of course, the change in temperature can easily be measured experimentally. And at the end of the experiment, once these 2 objects have reached some sort of equilibrium, the temperature of the final temperature, will be equal for both the surroundings and the system. Okay, so let's look at an example. A silver block, initially at 58.5 degrees Celsius, is submerged into 100 grams of water at 24.8 degrees Celsius in an insulated container. The final temperature of the mixture upon reaching thermal equilibrium is 26.2 degrees Celsius. What is the mass of the silver block? Okay, so this is a thermal energy transfer problem. You know that Q of silver block is going to be equal to the negative Q of the water. So we need to write out each one of these equations. So We want to find mass of the silver block, and we're given mass of water. So I'm going to write these out using the specific heat capacity, CS, for each. So we have mass of silver times the specific heat capacity of silver times delta T of silver is equal to the mass of water times the specific heat capacity of water times the change in temperature of water. We want to find the mass of silver, so we're going to rearrange this. Mass of silver is equal to the mass of water times the specific heat capacity of water times delta T of water, all divided by the specific heat capacity of silver times the change in temperature in silver. So we can use a table to find the specific heat capacity of silver and of water. And we're given the mass of water, we're given the final and initial temperatures of each. So it's a matter of just plugging in all of these values. So we have 100 grams of water times the specific heat capacity of water, which is 4.186 joules divided by grams times degrees Celsius. And then the change in temperature is the silver block is initially 50, or this is for water. The water is initially 24.8, and then it has a final temperature of 26.2. So this is going to be 26.2 degrees Celsius minus 24.8 degrees Celsius, all divided by the specific heat of silver, which is 0.239 joules divided by grams times degrees Celsius times delta T. So the final temperature is 26.2 degrees Celsius minus the initial temperature, which is 58.5 degrees Celsius. So I just realized I dropped the sign from the initial equation. So if you look up here, there's a negative sign in front of water, the Q of water. So I'm just going to add that in. I forgot to add it in. Okay. So that each one of these equal signs has a minus after it. Okay. So if you put this all in your calculator, you should get 76 grams of silver. I was using a specific heat capacity for silver that I just Googled, but I was just looking in your book, and actually the one in your book is 0.235 joules per grams times degrees Celsius, which is the correct value. I don't think I got this from a correct source, so don't just for your future problems, take my advice and don't Google things like I did. But if you did it with this correct value, you would get just a slightly different answer you would get 77 grams of silver. Okay, we spent a lot of time talking about Q, but now we need to talk about W a little bit. And what I said for you guys is that you only have to know conceptually what work is in this particular chapter. So work is the transfer of energy resulting from force acting over some distance, right, that makes the object move. We say that mathematically work is equal to negative pressure times the change in volume. So let's look at, I think that this is best done by looking at the two examples you might see. So you have an initial volume, it's 2 liters. You have a final volume, it's 3 liters. The pressure is the same, everything else is the same besides the work, or besides the volume. So if volume increases, that means that volume expands. This means for expansion, V final is greater than V initial. If that is the case, the sign of delta V is going to be positive, and the overall sign of work is going to be negative. It's going to be negative because from the formula you have that work is equal to the negative of P delta V. Let's consider the other condition. So you have volume 1 and then volume 2. This is contraction. And in this case, the final volume, which is volume 2, is less than the initial volume. This will make the change in volume sign negative, right? Because V final is less than V initial. The overall result that this has on work is that work is positive. Work is going to be positive because if you have a negative number times a negative number, that's a positive number. So what you have to remember is that when something expands, then that is a work done by the system on the surroundings, and that sign is negative. When contraction occurs, that is work done by the surroundings on the system, and the overall sign of W is positive. Okay, so now that we've thought about both Q and W, it's time to think about how these things are, how internal energy is measured experimentally. And so we're going to talk about two conditions, those that are under constant pressure and those that are under constant volume. So remember, the change in energy delta E is equal to heat plus the work. And we said that work is equal to negative P times delta V. We can rearrange this equation to say that the heat transferred from a particular reaction is equal to delta E plus P delta V. And you should think, why would we want to do that? Well, you know, changes in heat are easy to measure, right? It's easy to take a temperature reading. It's harder to measure pressure change in a reaction or volume change or something like that in a reaction. It's much easier to look at heat. So we like to, this is why we want to rearrange this equation, okay? So we're going to look at the heat transferred under a condition of constant volume and under constant pressure. At constant volume, the change in volume, V final minus V initial, will be 0 because V final and V initial are the same value. So Q then the heat transferred under constant volume is equal to the change in internal energy. And your book talks about two different experimental conditions where we're interested in constant volume or constant pressure. The one that's associated with constant volume is bomb calorimetry, and we'll talk about that in a minute. At constant pressure, however, the heat transferred is going to be equal to the change in internal energy plus pressure times the change in volume. And this is associated with coffee cup calorimetry, and this is what you're going to do in your lab. And so we can look at the heat transferred in a particular chemical reaction using either bomb calorimetry or coffee cup calorimetry. So previously we said that we can experimentally measure the change in heat of a process. And we said that at constant pressure, the change in heat of a particular process was equal to the change in internal energy plus P delta V. This quantity is referred to as enthalpy. So it's a heat flow during a particular chemical reaction. And so enthalpy, we use the letter H to represent enthalpy. And we say enthalpy is equal to energy plus the product of pressure and volume. So we can measure the change in enthalpy of a particular process occurring under constant pressure. And enthalpy is like the change in internal energy. The change in enthalpy is a state function. So we can write the change in enthalpy, delta H, as being equal to the change in both internal energy and the pressure volume work. Since this is at constant pressure, if we sort of distribute this delta here, then there's no delta P because the pressure is constant, so there's no change in pressure. And so we write this as the change in enthalpy, delta H, is equal to delta E, which is the internal energy, plus the pressure times the change in volume. So let's take a minute to consider what's different between delta H and delta E. Because you're probably thinking that they seem really similar, and they are. I mean, they both are state functions, and they both represent some sort of change in a particular system. The thing that's different about them, however, is that delta E is the measure of all of the energy exchanged with the surroundings, so both heat and work exchanged, whereas delta H is only a measure of the heat exchanged under constant pressure. So in practice, delta E and delta H are actually very similar, but in some conditions they're different. So in conditions where a large number of particles either are produced or consumed, like in a gas reaction, they might be different. But for other purposes, they're almost equivalent values. So let's consider what a change in enthalpy might look like. So let's consider the situation where heat is released from a particular system. So if we have enthalpy increasing, if you have some initial enthalpy and an enthalpy after a particular reaction, a final enthalpy, if the initial one is larger than the final one, then heat is going to be released because the change in enthalpy is going to be less than zero. Anytime heat is released from the system, we call this an exothermic reaction. So the system releases thermal energy, and the temperature of the system decreases because it gives heat to the surroundings. And let's look at the opposite case. So we have, again, enthalpy increasing. You have the system before a reaction, the system after the reaction. The system after the reaction has a higher enthalpy than the system before. This makes the change in enthalpy larger than zero, so heat is absorbed by the system. So the system absorbs thermal energy. This means that the temperature of the system increases and the temperature of the surroundings decreases. So let's apply this idea. We're going to determine whether or not each one of these processes is exothermic or endothermic, and we're going to figure out the sign of enthalpy. So let's think of A. A is natural gas burning on a stove. So natural gas burning on a stove is a combustion reaction. So in a combustion reaction, heat is going to be released. If heat is released, then delta H is less than zero. So that sign is going to be negative, and this is going to be an exothermic reaction. The system is releasing heat to the surroundings. So let's consider B, isopropyl alcohol evaporating from the skin. So isopropyl alcohol is just rubbing alcohol. So if you think about isopropyl alcohol and then the temperature of your skin, that isopropyl alcohol at room temperature and the temperature of your skin. The temperature of your skin is hotter, is warmer, right, than the isopropyl alcohol. So you put rubbing alcohol on your skin, your temperature of your skin is hotter than the isopropyl. So like the heat from your body is going to be put into that system. The system is the rubbing alcohol. So you have to add energy essentially in order for the isopropyl alcohol to evaporate. So delta H in this case is going to be greater than zero. It's going to be a positive value, and it's going to be endothermic. So let's think about water condensing from steam to the surroundings. So condensation is going to have an enthalpy less than zero. And so this is going to be an exothermic process. Okay, so now that we've talked about enthalpy a little bit, we need to think about the enthalpy of a particular reaction. So delta H is the change in enthalpy, and so we're interested in the enthalpy of the products minus the enthalpy of the reactants. Okay, so let's look at an example. So here we have this enthalpy diagram. We have methane and oxygen in one way yielding carbon dioxide and water. The delta H here, this is a combustion reaction, the delta H here is 890 kilojoules. So the negative sign tells us that's how much heat is released during the course of this reaction. If we consider the reverse of this reaction, going from carbon dioxide and water to methane and oxygen, then this 890 kilojoules has a positive value. It's telling us that that's how much heat energy would need to be supplied for this reaction to occur. So you notice that these are opposite in sign, but they're the same number. So this is an important thing about enthalpy. So you can reverse the sign to reverse the reaction. And you're going to have to pay attention to this, because oftentimes when you're doing calculations about enthalpy of a particular reaction, you're given some constant values, and you'll have to look at what reaction is happening. So let me give you an example to be more specific. So if you have methane plus oxygen gas yields carbon dioxide, gas plus water, and you're told that the enthalpy of this particular reaction is negative 890 kilojoules. And say you're asked, though, about the reverse of this reaction. What you have to know is that if you're doing this reaction in the reverse, that it's going to change the sign of this enthalpy of reaction. So this is a very important point. So please take note of it. There are a couple of other points about enthalpy that I'd like to make. So enthalpy, for example, is an extensive property. So if you want to review, we talked about extensive properties in Chapter 1. And in Chapter 1, we said that extensive properties depend on the amount of material or matter available. And so we said that, for example, mass, weight, volume, and length are all example of extensive properties. We said, however, that intensive properties are properties that do not depend on the amount of matter present. So we said things like density, boiling point, freezing point, conductivity, malleability, those sorts of things were intensive properties, so just to remind you. All right, also important about enthalpy is that the change in enthalpy for a particular reaction in the forward direction is equal to the sign, equal in size but opposite in sign to the enthalpy of the reverse reaction. We just saw that. That was the point I just made on the previous slide. Okay, and then finally, enthalpy for a reaction depends on the state of the products or reactants. So we just saw, it wasn't a reaction, but we just saw that condensation was an exothermic process. And so it's not that far of a stretch to think that the physical state, solid, liquid, or gas, is important in thinking about enthalpy. So when I said just a minute ago that enthalpy is an extensive property, what I mean by that is that when you have a particular chemical equation and you have an enthalpy of a reaction, if you increase the quantity of reactants and products, the enthalpy is going to increase by that same proportion. So let's look at this first reaction here. You have solid carbon plus oxygen gas yielding carbon dioxide. You have an enthalpy here of negative 393.5 kilojoules. This means that this much heat energy is released during the course of this reaction. It's an exothermic process. Now, this enthalpy is for 1 mole of solid carbon, for 1 mole of oxygen gas, and for 1 mole of carbon dioxide gas, right? And this is, I'm just looking at the, coefficients in front of each one of these reactants and products. If you were to double each one of these so that you had 2 moles of carbon, 2 moles of oxygen, and 2 moles of carbon dioxide, the enthalpy would increase by 2. So this is what we mean by this being an extensive property. If you increase the amount of matter that you're thinking about in a reaction, the enthalpy is going to increase by whatever proportion or whatever factor that you use. Okay? And again, if a chemical equation is reversed, the sign of delta H is changed. So here you have the forward for this reaction of carbon and oxygen to yield carbon dioxide. The reverse of this reaction, carbon dioxide decomposing into carbon and oxygen, is the same scale but a different sign. Alright, so let's look at an example of this. So we have the combustion of acetone, right, which is the main ingredient in nail polish remover. So acetone plus oxygen yields carbon dioxide and water. We have an enthalpy for this particular reaction. It's negative 1,790 kilojoules. If a bottle of nail polish remover contains 177 milliliters of acetone, we want to know how much heat is released by its complete combustion. And we have the density of acetone being 0.788 grams per milliliter. How you approach this problem is, in order to think about the enthalpy, you need to know the amount of acetone reacting. To find the amount in moles, we could go from milliliters, so we could go from volume to grams using the density, and then we can go from grams to moles using the molar mass. Then we could multiply this amount by the delta H of the reaction, and that will give us the heat released from 177 milliliters of acetone. Alright, so let's solve this problem. Oops. So we have 177 milliliters of acetone. For every 1 milliliter, there's 0.788 grams. Acetone's molar mass is 58.08 grams for every 1 mole of acetone. Let me put this in my calculator. So I get 2.40 moles of acetone. So to find the heat released by combustion, I'm going to multiply this by the delta H of the reaction, and I get negative 4,298 kilojoules. Okay, before I defined enthalpy, I had mentioned that there were 2 experimental ways to look at the heat transferred or given off in a particular reaction: bomb calorimetry and coffee cup calorimetry. We said bomb calorimetry was at a constant volume. And so in bomb calorimetry, you have like some sort of reservoir, and you filled it with water, and then you have another reservoir, and you have a little sample in that second chamber. It's the bomb chamber, and you put whatever your sample is, your material is, in there, and then you essentially combust it, and you can measure the heat absorbed by the surrounding water. And then that gives you an approximation of the change in enthalpy for that particular reaction. And so we say that the heat transferred in the reaction is equal to the heat capacity of the calorimeter times the change in temperature. The heat capacity of the calorimeter is going to differ depending on each individual calorimeter, and so it's a value that needs to be determined experimentally, and it's considered a constant for whatever particular apparatus that you're using. So again, bomb calorimetry has constant volume, and so what's measured is, if you remember, if we rearrange this equation, Q is equal to delta E delta E plus P delta V. At constant volume, right, this term goes to 0. So the heat change is really the change in internal energy, not enthalpy. But since internal energy and enthalpy, for most cases, are going to be very similar values, the actual difference would be very small. Okay, so let's talk about constant pressure calorimetry, and this is what you're actually going to do in lab. So in coffee cup calorimetry, you have some sort of insulating material. You have maybe like a lid that fits on that insulating material, and you have some sort of reaction mixture in this insulated cup. Usually you use 2 styrofoam cups. It's not high-tech or anything like the bomb calorimeter. And then you have some sort of stir and a thermometer. So you can look at the heat change in this system by measuring the heat change but with the thermometer. And so you know the specific heat for water, and so you can calculate the enthalpy for this reaction using the equation that we learned earlier, which is that heat, Q, is equal to the mass times the specific heat times the change in temperature. So let's look at an example. So when 0.514 grams of biphenyl undergoes combustion in a bomb calorimeter, the temperature rises from 25.8 degrees Celsius to 29.4 degrees Celsius. We want to find the delta E for this reaction for the combustion of biphenyl. And we want to find this in kilojoules per mole. The heat capacity of the bomb calorimeter determined in a separate experiment is 5.86 kilojoules per degree Celsius. So here's something that's important. We want to find this in kilojoules per mole. So we know that bomb calorimetry is under constant volume, and so the heat of combustion is going to equal the heat capacity of the calorimeter times the change in temperature. This is going to give us the internal energy of this reaction, the change in internal energy in kilojoules. We want then to look at this mass of biphenyl, this amount of biphenyl. So we need to find the moles of biphenyl, and what we'll do is we'll divide the kilojoules that we find by the moles. Alright, so let's solve this. We have the heat capacity of the calorimeter, and we have delta T. So let's just plug this in. We have 5.86 kilojoules per degree Celsius for our heat capacity of the calorimeter. We're going to multiply this by delta T. Delta T is T final minus T initial. Okay, so when we do that, we get 21.096 kilojoules. Okay, so that's the delta E in kilojoules, but we need to find it for this very specific amount. So we have, I'm going to find the moles of biphenyl that we have in this particular reaction. We have 0.514 grams of biphenyl, C12H10. Biphenyl has a molar mass of 154 grams for every 1 mole. And so we have 0.0000334 moles of biphenyl. Delta E of the reaction in kilojoules per mole then is going to be 21.096 kilojoules divided by 0.000. I think I have one too many zeros there. Oops. 0.00. .334 moles. If you divide these two, you get 6,316 kilojoules per mole. So that's how much internal energy, the change into internal energy for this particular reaction.